This is Physics 211, Lab 4. Table of contents, we're going to talk about the introduction, some physics concepts, look at the tracker, look at our code with oscillations model, compare this data, and then look at some possible sources of error and some additional questions. So for the introduction, the purpose is to observe and study the motion of an oscillating object and compare real data from tracker to a model. Our physics principles are Newton's second law, the energy principle, position and velocity update formulas, and then kinetic, gravitational potential, and spring potential equations. And the outcome is that we set the system as the hanging object, the spring, and the earth. And then the model data lines up close to the real data, except without losing any energy to the surroundings. The energy graph can then be analyzed to see the position of the spring and the model. For Newton's second law, it states that when a force acts on an object, it will cause it to accelerate, and there's our equation. And then for the energy principle, we know that energy cannot be created nor destroyed, and we know that work plus heat is going to give us total energy. And then for our actual energy equations, you'll see that in the code. So for our tracker data, took about 9 seconds. It was 105 data points. The initial velocity is and initial position were both derived from the code, but I put the initial position here anyway. And then we have our system is the hanging mass, the spring, and the earth. So for our oscillation model code, on the far left is our initial conditions. We have the ball mass given from the video, the delta t given from the video, and then our ball dot position and ball dot vector are pulled directly from the CSV file. So G is 9.8. Our spring constant is 6.83, also from the video, and our L naught is 0.123, which is also from the video. We then have our L, which is equal to ball dot pos minus spring dot pos, our L hat, which is L over magnitude of L, and then S, which is magnitude L minus L naught, to set up basically all of our spring values. Down here is our actual energy equation. So we have kinetic energy, it's 1/2 times the mass of the ball times the magnitude of the ball's velocity squared. For gravity, it's the mass of the ball times gravity times the position in the y, the ball position in the y. And then for US, it is going to be 1/2 Ks and then S squared. So that's going to be for our spring potential. And then total energy just all is added up. So for our actual calculation loop, we set Ki to just be what those numbers are to begin with. We set gravity to be the gravity vector, so negative ball dot m times g, and then our F spring, which is just the equation, and then our F is that together. Then we have our velocity and position update formulas, the spring values for the actual loop, and then the bottom we have our energy equations, and then the change in K is just that minus whatever the initial was. So that's actually giving us our changing values. So when we compare the two data sets, we have two graphs. One on the left is for the X, one on the right is for the Y. So on the X one, you can see both of them line up a lot. Now in the X, you're going to see that there's not too much of a fall off. And in the model experiment, typically stay very close together. But in the Y, you see a little bit more of a fall off, and that's mainly because the spring is losing energy in the experiment, while the model doesn't actually have any way to lose energy. It is constant. And which we can actually see some possible sources of error here, which is what we talked about, energy loss to surroundings. In reality, some energy lost due to heat or in other ways, and then this is not measured in our model, so it keeps the constant oscillations. And then some tracker imprecision could also cause some issues here, which is probably why you might see the starting humps being a little different. And then this is our change in energy graph. See all the different stuff, delta K, delta U graph, delta U spring, and then our energy, you see, is a constant line, which is how we answer this question, which is the energy principle satisfied? Well, in this case, yes, it is satisfied. No external forces are acting on the system in the model, so the change in energy is 0. And even though there are multiple types of energy in the system, if you look at the orange line, which represents total energy, it is constant, which means it does actually satisfy the energy principle. And then for the next question, which is the period of oscillations, so we can take one from the X and one from the Y. So when we calculate these numbers out, for the X, we end up getting a different number than the Y. The Y is actually a greater number, but this actually makes sense when you think about it. And since the numbers are different, this means picking the different directions does affect the spring constants in the graph. So if you choose to analyze in the X or Y, you won't necessarily get the same answers. So that is the end of this lab video. Thank you for watching.